Hey, you're here. That already tells me two things about you. One, you probably like math, or at least you're curious about it. And two, you're either trying to fall asleep or procrastinate. Either way, you've come to the right place. This is the Sleepless Mathematician, and tonight we're going to take a very slow, very strange journey into the minds of some of the most brilliant people who ever lived. People who played with numbers like toys and sometimes paid a heavy price for it. We're talking about the kind of geniuses who didn't just solve problems, they became the problem. They duelled with pistols over algebra. They saw infinity and lost their minds. They cracked the secrets of the universe, and then cracked themselves. But don't worry, this won't be one of those dry math lectures with Greek letters flying everywhere like confetti. No formulas tonight, just stories. Some beautiful, some tragic, some completely absurd. You don't need to remember anything here. In fact, I hope you forget most of it. That means I did my job right, because this channel isn't just about math. It's about gently slipping into sleep, with a bit of wonder, a few laughs, and a lot of strange little facts. Now, I want you to imagine something. You're 20 years old. You've just discovered a new branch of mathematics that explains how equations behave. It's groundbreaking, like Nobel Prize level, but for math. And tomorrow morning, you're going to die in a duel. Sounds fake, right? But that's exactly what happened to Évariste Galois, a French mathematician with a name that sounds like an expensive wine, and a brain that worked faster than most people blink. He wrote down a mathematical theory the night before he died, because he knew what was coming. And that's just the beginning. In this video, we're going to meet minds like his. People who solved the unsolvable, chased perfection, and often paid for it in the weirdest possible ways. You'll hear about Gödel, who proved that math is incomplete, and then refused to eat because he thought someone was trying to poison him. You'll meet Georg Cantor, who invented infinity as a math concept, and spent most of his later life arguing with priests and slowly unravelling. We'll visit Alan Turing, who broke the Nazi codes and basically invented computers, only to be punished by the very country he helped save. And then there's Ramanujan, who said the goddess of mathematics whispered equations into his dreams. Honestly, same. These people were not normal, which is why they're fun to talk about, or whisper about, because maybe you're already getting sleepy. That's good. Each story in this video is like a math bedtime fable. Some are sad, some are hilarious, some are so bizarre you'll think I made them up. I didn't. Math history is way weirder than fiction. We'll talk about the equations. Sure, but mostly we're going to talk about the people, the messy, brilliant, chaotic people behind the symbols. Because math doesn't come from nowhere. It comes from brains. Beautiful, complicated brains. And those brains sometimes broke. Like, dramatically. Some of them died young, others died weird. Some were never appreciated until after they were gone. And a few, honestly, were kind of insufferable, but we still owe them everything. And if you're thinking, okay, but why would someone literally die over an equation? Well, good question. That's what we're here to find out. So, just let your body sink into whatever you're sitting or lying on. Get cozy. Maybe let your eyes drift a bit. There's no test at the end of this. Just strange stories delivered slowly, like a very nerdy lullaby. We'll start with Galois, the angry French genius who got expelled, arrested, insulted every professor he met, and then right before getting shot, wrote down an equation that changed mathematics forever. But that's in the next chapter. For now, just breathe. You're officially entering the peaceful, bizarre world of mathematical madness. Let's talk about Évariste Galois, or as I like to call him, the most dangerous algebra nerd in history. He was born in France in 1811, a time when being really good at math didn't exactly protect you from duels, revolutions, or, well, anything really. His dad was a schoolmaster and political activist. His mum taught him Latin and Greek. Basically, Galois grew up surrounded by arguments, books, and probably some extremely passive-aggressive dinner conversations. By the time he was a teenager, Galois was already smarter than most of his teachers. And that's not me exaggerating. He actually got kicked out of school for being too intense. Imagine being so good at algebra, they ask you to leave. Now Galois wanted to get into École Polytechnique, the top math school in France. He applied. He failed. Twice. Why? Because during the exam, instead of doing what he was told, he basically invented a new way of thinking about equations. The examiners didn't get it. Classic too smart for the room situation. Eventually, he ended up at a lesser-known school where he annoyed almost every professor. He'd correct their lectures mid-class, loudly, with footnotes. No one liked that, except maybe future math historians, who were eating this up. Around this time, France was in political chaos. Again, Galois, of course, joined a radical Republican group. He wore black. He talked revolution. He probably sighed dramatically a lot. He even got arrested for raising a toast to the king, with a dagger in his hand. The police were not amused, but in between arrests, expulsion threats, and a lot of glaring at authority figures, Galois did something incredible. He laid the foundation of what we now call group theory. He discovered a way to understand the symmetry of equations. It's called Galois theory. And yes, they named it after him. It basically tells you if a polynomial equation can be solved using basic operations like addition, multiplication, and roots. Spoiler, not all of them can. Galois figured all of this out in his early 20s. Most of us were still figuring out how to microwave noodles without spilling. But Galois, he was solving problems that had haunted mathematicians for centuries. Then came the duel. And here's where the story gets blurry, because no one really knows exactly why he was challenged. Some say it was over politics, others say it was about a woman. There's even a theory that it was a setup. Whatever the reason, Galois knew it was coming. The night before the duel, he didn't sleep. He wrote. He scribbled down everything he could remember about his theory. He had to get it out before he died. His last words on paper: mathematical genius under extreme pressure. Imagine speedrunning your entire life's work with one night left. He wrote to his friend, "I have no time, and then I hope someone will find something of value in what I've written." He walked out at dawn, met his opponent, and was shot in the stomach. He died the next day, at just 20 years old. And the papers, the ones he wrote that night, they sat ignored for years. No one understood them, not at first. It wasn't until years later that mathematicians realized what he had done. Galois' theory became one of the pillars of modern algebra. Think about that. He discovered something that's now taught in universities all over the world, and he did it between prison stays, political revolts, and being wildly underappreciated by basically everyone. There's this poetic tragedy to his story. He was angry, brilliant, misunderstood, and probably insufferable at parties. But he saw math in a way no one else did. He didn't just solve problems, he reinvented the rules. Also, let's just acknowledge the absurdity here. He might have died over a love triangle, or for insulting the wrong person. Imagine losing one of the greatest math minds because of a bad breakup. That's the level of chaos we're dealing with. So next time you're frustrated with math, just remember, at least it hasn't gotten you shot yet. Évariste Galois lived fast, thought deep, and died young. But his ideas, they lived on. And today, every time someone studies algebraic equations, they're walking in his footsteps, hopefully with fewer duels involved. Let's keep going. Things are about to get even weirder. In the next chapter, we'll talk about the most important letter ever written in math, written in a panic, with a bleeding stomach, just hours before death. Because that's totally normal math history, right? So, the night before Évariste Galois died, he didn't cry, he didn't run, he didn't beg for his life. He did what any emotionally stable 20-year-old would do when they know they're about to die. He stayed up all night doing math seriously. He knew the duel was coming. He had seen enough red flags to wallpaper the Eiffel Tower, and yet, instead of panicking, he locked himself in a room with pen and paper and tried to download his entire brain onto a few sheets before dawn. What he produced that night would later be called the most important letter in the history of mathematics. Not because it was long, not because it was polished, but because inside those scribbled pages, Galois laid out the core ideas of what would become modern algebra. Let's pause and think about that. He had one night, no laptop, no coffee machine, just raw desperation, and a mind moving at full speed. And instead of writing something like, "Tell my mother I love her," he's writing about solvable polynomials and permutations. That's commitment. The letter was addressed to a friend, Auguste Chevalier, who was also a math enthusiast. Galois basically told him, "Hey, I'm probably going to die tomorrow. Here's everything I've been working on. Please get it published if it makes any sense at all." Now, the tone of the letter? It's frantic. You can feel the urgency in every sentence. He uses phrases like, "I don't have time," and "I can only scratch the surface." Imagine someone trying to explain years of work, all in a single sitting, with a ticking clock and a loaded pistol waiting for morning. And the math itself, well, it was revolutionary. Galois described how the roots of a polynomial are connected by symmetry, and how you can use group theory to know whether an equation is solvable by radicals. This would later shape fields like abstract algebra, cryptography, and even quantum physics. But here's the sad part. After Galois was shot and died, the letter didn't exactly go viral. In fact, it got ignored. For years, Chevalier tried to publish it, but no one really understood what Galois had done. The handwriting was messy. The logic was dense. The ideas were about 50 years ahead of their time. It wasn't until the 1840s, over a decade after his death, that mathematicians started going, "Wait a second, this Galois guy might have been onto something." One of the people who picked it up was Joseph Liouville, a well-known mathematician. He read through Galois's chaotic scribbles and realized it wasn't nonsense. It was brilliance. He cleaned it up, edited it, and finally published the work in That's 15 years after Galois had bled out in a ditch. 15 years for the world to catch up to a 20-year-old kid writing math at 3 in the morning before getting shot. And the craziest part? He was right. The ideas in that letter laid the groundwork for a huge part of modern mathematics. Galois theory is now standard material in advanced algebra courses. It helps explain which equations can be solved, and which ones are just too chaotic. It's also the foundation for fields that Galois never lived to see. Cryptography, for example. Your bank account is protected by encryption that traces its roots, in a weird way, back to that frantic letter. Think about that next time you use online banking. Somewhere in the code that protects your money, there's a little piece of a dying French genius whispering from it. But let's zoom out for a second. What kind of person does this? What kind of mind, faced with death, chooses to write a math paper instead of, I don't know, running away, or writing a sad poem? Galois wasn't just brilliant. He was obsessed. He saw math as more than numbers. It was structure, truth, order, in a world that made no sense, especially to someone as politically and emotionally chaotic as him. And in a strange way, that last letter wasn't just math. It was his will, his goodbye, his legacy, wrapped in symbols, equations, and frantic handwriting. We rarely talk about math as emotional, but it is, especially here. That letter is one of the most dramatic, desperate, and beautiful things ever written in mathematics. Because behind the theory there's a human being who knew he was running out of time. And he used that time not to cry or complain, but to build something. Something that would outlive him by centuries. Now, when students today struggle with Galois theory and say, who came up with this? The answer is, a 20-year-old bleeding out with a pen and a dream. So if you ever feel like you're behind in life or not smart enough, just remember, Galois was ahead of his time, misunderstood, and died thinking no one would ever read his work. But they did. Eventually. And they were amazed. Next up, we're going to zoom out a little and ask the obvious question, why were 1800s French math geniuses always getting into duels? Because algebra is dangerous. Apparently, okay, let's address the obvious question. Why were French mathematicians always getting into duels? Seriously, Évariste Galois wasn't even the only one. 19th century France had this weird energy where doing math was somehow connected to throwing down your gloves and demanding satisfaction. If you were young, political and good with equations, odds are you were also practicing your dramatic pistol pose in the mirror. Now, to be fair, France at the time was basically living in permanent revolution. The government changed more often than most people changed their socks. You had royalists, republicans, Bonapartists, and everyone in between, all constantly yelling at each other in very poetic French. Galois fit right into this mess. He wasn't just a mathematician, he was a loud, proud revolutionary. He joined secret societies, wrote angry essays, and gave public speeches that definitely did not include the phrase, "let's keep things civil." And he wasn't quiet about his political views either. One time, at a banquet, he raised a glass to the death of the king while holding a dagger. That's not a metaphor. He literally toasted with a weapon in his hand. It's a miracle he didn't get arrested on the spot. Oh wait, he did. So how does this lead to a duel? Well, the historical record is fuzzy. Some say it was a political dispute. Others think it was about a love triangle involving a woman named Stephanie. A few even suspect it was a setup. Someone wanted him gone, and a duel was the perfect excuse. But whatever the reason, Galois accepted the challenge, which again was kind of normal at the time. Duels were technically illegal, but also weirdly respected. Like, yes, this is against the law, but also good luck, sir. It's worth pointing out that Galois wasn't exactly trained in combat. He wasn't a soldier. He wasn't an athlete. He was a 20-year-old math genius who spent most of his time arguing with professors and scribbling equations in candlelight. Still, he showed up. Early morning, quiet field, second in command. The whole dramatic movie scene. He even brought 2 loaded pistols. And here's the part no one agrees on. Some say he deliberately missed his shot. Others say he was nervous, or just a bad aim. We'll never know. What we do know is that he was shot in the stomach. He didn't die right away. He was taken to a hospital. But they couldn't save him. He passed away the next day, and just like that, one of the brightest mathematical minds of the century was gone. Now, let's pause for a second and talk about how deeply unnecessary this all was. He didn't die in a lab. He didn't die of illness. He died in a muddy field because someone said something that made someone else mad. And algebra was never the same again. If this sounds dramatic, that's because it is. But it wasn't unique. The 1800s were full of dramatic math people. Everyone had strong opinions, bad tempers, and a tendency to carry weapons. It's like academia but with muskets. Galois himself wasn't an easy person. He was passionate, brilliant, and impossible to manage. He'd attack professors in public letters. He refused to explain himself simply. He believed he was right, even when no one else could follow. And often he was. The duel is just the most cinematic moment in a life full of chaos. But it also represents something bigger. The idea that math isn't some peaceful, quiet field full of bearded guys mumbling into blackboards. Sometimes it's political. Sometimes it's passionate. Sometimes it gets people killed. So the next time someone says math is boring, feel free to tell them about the guy who invented group theory and died in a duel before his 21st birthday. That usually changes the mood at parties, and in a strange way, the duel made Galois immortal. Not just because of the tragedy, but because of what he left behind. The night before he was shot, He wrote down ideas that would take the rest of the world decades to understand. That kind of brilliance, paired with that kind of ending, turns a person into a legend. He became the James Dean of mathematics, the Mozart of polynomials, the guy who looked at the world, said you don't get me, and proved it in a blaze of genius and bullets. Was it worth it? No, definitely not. We could have used a few more decades of Galois, but the story? It stuck. And maybe that's why people still care. So yeah, maybe don't mix advanced math with French revolutionary energy and access to firearms. It rarely ends well. Next, we're going to talk about a guy who didn't die in a duel, but probably wished he had. Because he invented infinity, and then spent the rest of his life being called crazy for it. Let's meet Georg Cantor. Alright, let's talk about infinity. Not the vague, dreamy, poetic kind. The real, terrifying, mathematical kind. The kind that breaks your brain a little. And the man who gave us that kind, Georg Cantor. Now, infinity had existed in philosophy forever. The Greeks thought about it, the church feared it, poets loved it, but nobody really defined it. Not like Cantor did. Georg Cantor was a German mathematician born in 1845, which means, for reference, that he came into the world about a decade after Galois died. Totally different vibe. Much more Prussian. Fewer duels. Slightly more tweed. Cantor grew up in a musical family. His dad wanted him to be a violinist, and George probably could have done it. But instead, he got stuck on the idea of how big is infinity. Seems simple, right? Infinity is infinity. End of story. But Cantor wasn't satisfied with that. He wanted to compare infinities, measure them, count them, which is hilarious when you think about it. Counting the uncountable. Classic math guy move. So here's what he did. He started thinking about sets, groups of numbers, and he realized something strange. The set of natural numbers like 1, 2, 3, and so on was infinite. Okay, we knew that. But the set of real numbers, like every possible decimal, that was more infinite. Wait, what? How can something be more infinite than infinite? Exactly. That's what blew everyone's mind. Cantor proved, using actual math, that there are different sizes of infinity. Some infinities are bigger than others. He showed that the real numbers can't be matched one-to-one with the natural numbers. There are just too many of them. Infinite plus, this was like dropping a philosophical nuke into the math world. People were not ready. They didn't just reject his ideas. Some called him a heretic. Others said he was ruining math. One famous mathematician, Leopold Kronecker, literally spent years trying to destroy Cantor's reputation. And the irony, Cantor was right. We now know he was completely mathematically correct. But during his life, that validation was slow and painful. Cantor kept working. He invented set theory, cardinal numbers, transfinite numbers. He showed that the concept of size could be applied to infinite sets, but the backlash wore him down. He started to struggle, not just professionally, but mentally. He had breakdowns. He was hospitalized. At one point, he became obsessed with proving that Francis Bacon wrote Shakespeare's plays, which is a wild pivot. But honestly, after inventing infinity, I can't blame him for wanting a hobby. People around him started saying he was unstable, difficult, dramatic. But really, he was just a man who had stared too deeply into the abyss of numbers. And the abyss stared back. Imagine that. You discover one of the most important concepts in modern mathematics. And your reward? You get ridiculed, discredited, and quietly shuffled off to a mental institution. Today, Cantor is seen as a genius. Set theory is one of the foundations of modern mathematics. Infinity, thanks to him, is something we can talk about, argue over, and actually use. Computer science, physics, logic, they all owe something to Cantor. But during his life, he was mostly seen as a problem, a threat. a little too radical, a little too loud, a little too infinite. It's funny, the church didn't like Cantor's ideas either, because if there are levels of infinity, then what does that say about God, about heaven, about the soul? His math wasn't just challenging other mathematicians, it was poking at centuries of theology. Cantor, by the way, was religious. Deeply. He thought infinity was a window into the divine, that mathematics was a way to understand the infinite mind of God. The math wasn't just numbers, it was spiritual, and honestly, that makes sense. You don't chase infinity unless you believe in something bigger than yourself, or at least something weirder than yourself. So let's recap. Georg Cantor invented modern infinity. He proved that some infinities are bigger than others. He founded set theory. He shaped the future of math. And in return, he got depression, enemies, and very little recognition. If math had a martyr, it would be Cantor. No duel required. Next, we're going to check into a very strange hotel, one with infinite rooms, infinite guests, and 0 vacancies. It's one of Cantor's weirdest legacies, and it starts with a man named Hilbert, and a very long hallway. Coming up, the hotel with infinite rooms and no vacancies. Alright, let's check into the weirdest hotel you've never stayed at. A hotel with infinite rooms, infinite guests, and somehow no vacancy. Welcome to Hilbert's Hotel. This idea was created by David Hilbert, another brilliant German mathematician who loved blowing minds for fun. He used it as a thought experiment to show just how bizarre infinity really is. And yes, it's technically fiction, but it's math fiction, which makes it cooler. So imagine this. There's a hotel with an infinite number of rooms, like room 1, room 2, room 3, all the way forever. And every single room is full. Everyone. No vacancies. So naturally, someone new shows up and wants to check in. Now, in a normal hotel, this would be a problem. But in Hilbert's hotel, the manager just shrugs and says, "No problem, we'll make space." Here's what they do. They ask every guest to move one room over. Room 1 goes to room 2. Room 2 goes to room 3. Room 3 to room 4. And so on. Since there's no last room, this process never stops. But it can be done. And just like that, room 1 is now empty. Boom. A new guest checks in. Problem solved. That's the magic of infinity. But wait, it gets weirder. Let's say a bus pulls up, and it's not just one new guest, it's an infinite number of guests. Infinite passengers, all labelled with numbers, like passenger 1, passenger 2, and so on. Again, every room in the hotel is already full, but the manager just smiles and says, "We've got this." He asks every current guest to move to the room that's double their current number. So room 1 goes to room 2, room 2 to room 4, room 3 to room 6. Now all the odd-numbered rooms, room 1, 3, 5, 7, are empty, and there are infinite of them. So all the new guests from the bus can be checked in easily. Each one gets an odd room. So what just happened? The hotel was full, then it got more full. And yet somehow, everyone got a room. That's infinity logic for you. And it doesn't stop there. You can send an infinite number of infinite buses, with infinite passengers each, and Hilbert's Hotel will still find a way to check everyone in. You just need clever math and no fire code. It's absurd. It's hilarious. And it's completely consistent within the rules of infinity. This thought experiment isn't just a fun mind game. It actually helps explain real ideas in set theory and logic. It shows how infinite sets behave in ways that break our normal human intuition. In real life, infinity doesn't work like this. Your local hotel has like 30 rooms and a broken vending machine. But in math, infinity plays by different rules. Hilbert's Hotel shows that infinity isn't just big, it's structured. It can be manipulated, it can be used, and that makes it powerful, and also a little terrifying. Cantor's work laid the foundation, but Hilbert gave it a lobby, a front desk, and a weirdly enthusiastic manager, and that image stuck. People love this hotel. It shows up in philosophy, cosmology, even sci-fi. Some people use it to argue about the universe. If the cosmos is infinite, is it like Hilbert's hotel? Can it stretch forever and still make space for more stuff? Others use it to talk about time. Like, if there were infinite past moments, how did we ever get to now? Wouldn't we be stuck moving guests around forever? It's wild that a fictional hotel has sparked so many serious discussions, but that's what good math does. It sneaks up on you, dressed as a joke, and then changes how you see everything. And maybe that's why Hilbert's hotel is still famous today. Not because anyone's staying there, but because it reminds us that math isn't always about solving things. Sometimes it's about breaking reality in just the right way. So if your brain hurts a little right now, don't worry, that just means you're thinking in infinite terms. Congratulations, you're now a guest of Hilbert's Hotel. Next time we'll shift from hotels to paradoxes, because infinity wasn't done messing with people. In fact, for one guy, it might have gone a little too far. Coming up, how infinity drove him mad, and the church didn't help, so we've checked into Hilbert's Hotel. Now it's time to meet the guy who built the concept behind it. The one who stared deepest into infinity and didn't exactly come back okay. Georg Cantor. Yes, we've already met him, but we need to dig deeper, because infinity didn't just make him famous. It might have broken him. Cantor's theory of multiple infinities wasn't just revolutionary, it was heresy, not religious heresy. Well, actually kind of, but also mathematical heresy. See, his main opponent, Leopold Kronecker, didn't believe in actual infinity. He thought math should be about things you can count. You know, real, whole, nice little numbers. Anything else was nonsense, and he made sure everyone knew it. Kronecker had influence. He used it to block Cantor's papers from being published. He publicly mocked him, privately undermined him. He was basically the academic version of a schoolyard bully, with tenure. Imagine inventing an entire new mathematical universe, only to have the principal say, "Yeah, we don't like your attitude." Cantor tried to keep going, but rejection after rejection wore him down. His letters got darker, his tone got more defensive, and eventually his mental health began to fracture. He had episodes, long periods where he couldn't work, couldn't write, couldn't think clearly. He'd check himself into sanatoriums, rest, recover, then dive back into the math again. It was a cycle. Inspiration, obsession, collapse, and through it all, Cantor became obsessed with proving something else. Not about math, but about literature. He became convinced that Francis Bacon had written the plays of William Shakespeare. Now, was that true? No, almost definitely not. But it became a distraction, a way to escape the stress and attacks he faced from the math world. A new puzzle to solve, one that didn't involve people telling him he was crazy for a while, at least. The irony is, many of the same people who mocked him for his delusions about Shakespeare had spent years mocking him for his very real, very correct math. So, who's the crazy one, really? Meanwhile, the church started noticing his work too. Cantor saw infinity as a divine idea. He thought his work was a way to understand God. He even wrote things like, "The essence of mathematics lies in its freedom." But some theologians didn't like this. They worried that if infinity could be measured, compared, labelled with Greek letters, maybe it wasn't divine anymore. Maybe it was just numbers. That scared people. So now he wasn't just being attacked by mathematicians, he was getting side-eyes from theologians too, which is a lot to deal with, especially for someone already teetering. Cantor went back and forth between institutions and home. He never gave up on math, but he also never fully recovered. His later years were marked by isolation, poverty, and frustration. He died in 1918, alone in a mental institution during a time when the world was dealing with war, disease, and chaos. His work was barely recognized, and yet, here we are, talking about him, using his ideas, teaching his theories to generations of students. Set theory is foundational now. Infinity is a serious subject in modern math. Georg Cantor is remembered as a pioneer, a rebel, a genius who saw beyond the limits of what math was supposed to be. But during his life, he was a threat, a nuisance, an outsider. He was the guy who thought too big, too weird, too infinite. So did infinity drive him mad? Not exactly. The math didn't break him. The people did. The rejection, the ridicule, the isolation. That's what pushed him over the edge. And maybe that's the most heartbreaking part of his story. Not just what he discovered, but what it cost him to discover it. So the next time someone says infinity's not that deep, just tell them this story. Then hand them a set theory textbook and wish them luck. Coming up next, we'll shift from madness to logic. But not just any logic. The kind that proves math can't prove itself. Time to meet Kurt Gödel, the man who broke mathematics with logic. It's time to meet a man who didn't just think outside the box. He quietly set the box on fire, stared into the flames, and whispered, "Actually, this box was never provable to begin with." Kurt Gödel, a name that sends shivers down the spine of anyone who's ever taken a logic course. Born in 1906 in Austria-Hungary, Gödel was a quiet, brilliant, slightly mysterious figure from the very beginning. They called him Mr. Why as a child because he asked questions about everything. Why this? Why that? Why does math work? Why does logic work? Why are we here? Honestly, good questions. He studied in Vienna and became part of a group of hardcore logical thinkers known as the Vienna Circle. Their goal? To rebuild knowledge from the ground up using reason, logic, and good coffee. Probably. Gödel, though, had other plans. While the rest of the circle was trying to make math perfect and complete, Gödel was quietly proving that it couldn't be done. In 1931, he published what is now known as the incompleteness theorems. And yes, that sounds intimidating, but let me break it down in the chillest way possible. Basically, Gödel showed that in any consistent mathematical system that's powerful enough to describe basic arithmetic, there will always be true statements that you can't prove. Let me say that again, slower. There will always be true things that can't be proven. That's wild. That's like walking into math class and being told, "Hey, we're pretty sure this thing is true, but we can never actually prove it. Good luck." The second theorem goes even deeper. It says that a system can't prove its own consistency. So even if your math system looks solid, you can never prove from within that it won't eventually blow up. It's like trying to lift yourself off the ground by pulling on your own shoelaces. Gödel's work was a mathematical bombshell. People didn't know what to do with it. It undermined the dream of a perfect, complete math system, something thinkers like Bertrand Russell and David Hilbert had been chasing for decades. It was like someone had just walked into the cathedral of logic and yelled, "This place is termites." But Gödel wasn't trying to destroy math. He was just telling the truth. A very precise, unshakable truth that made everyone extremely uncomfortable. Strangely, Gödel didn't seem thrilled by the fame. He was shy, reclusive, and extremely careful about his health. Like, extremely. He was convinced people were trying to poison him. He would only eat food prepared by his wife. If she was away, he didn't eat. And yet, he was friends with Albert Einstein. The two of them would take long walks together, talking about math, time, and probably how annoying people were. Einstein once said that going to the Institute for Advanced Study in Princeton wasn't about science anymore. It was so he could walk with Gödel. That's how much he respected him. But despite his genius, Gödel was deeply troubled. He grew increasingly paranoid, reclusive, terrified of illness, of contamination, of the world falling apart. He eventually starved to death. Literally, his wife was in the hospital. No one else could prepare his food, and he simply stopped eating. He weighed about 65 pounds when he died, and yet his mind was one of the heaviest in history. Today, Gödel's incompleteness theorems are central to math, logic, and computer science. They tell us that there will always be limits, always truths we can't reach, always uncertainty at the edges. Some people find that terrifying, others find it beautiful. It means that even in the most precise field mathematics, there's still mystery, still wonder. Gödel proved that perfection is impossible, and that's oddly comforting, because it means we don't have to find all the answers. Some things are meant to stay just out of reach. Coming up next, Gödel's strange ending continues. What happens when you're too logical for your own good? The man who broke math now breaks reality. Let's be honest. No one expects to hear starve to death in a story about math, but with Kurt Gödel, nothing about his life followed the rules. Not even the ending. By now, you know Gödel was brilliant. A logic machine in human form. But that machine was fragile. It ran on strict routines, constant anxiety, and one very patient wife named Adele. Gödel's paranoia started small. He worried about getting sick, about eating bad food, about being poisoned, which, okay, fair, the 20th century wasn't exactly bacteria-free, but Gödel took it to another level. He wouldn't eat food prepared by anyone except Adele. Not restaurants, not family, not even colleagues. If Adele made it, he'd eat it. If she didn't, he'd starve. This sounds extreme, and it was, but it wasn't coming from vanity. It came from fear, deep, all-consuming fear. Gödel trusted math more than people. Numbers didn't lie, humans might. As he got older, the fear got worse. He became more isolated, refused medical help, locked himself in intellectual loops, writing pages of notes about conspiracies, secret plots, imagined illnesses. Still, people around him tried to help. Einstein visited, colleagues checked in, but Gödel kept slipping further into himself, into logic, into fear, into silence. Then, one day, Adele fell ill. She had to be hospitalized. Nothing too unusual, just enough to keep her away for a while. But for Gödel, it was catastrophic. With Adele gone, no one could prepare his meals. No one he trusted. He stopped eating. Days passed. Then weeks. People offered food, offered to help. But he refused. If Adele didn't make it, he wouldn't touch it. He became weaker, and thinner, and quieter. Eventually, he was taken to the hospital. But it was too late. Kurt Gödel died of starvation in 1978. Weighed barely 65 pounds. One of the sharpest minds in history. Starved not by poverty, but by logic. Pushed to the edge. It's one of the most tragic endings in science, and also one of the strangest. He didn't die in an experiment, or in exile. He died because his logic didn't know when to stop. Gödel once proved that in any system, there are things that can't be proven. That's what made him famous. But maybe he also proved something else, that when logic tries to explain everything, it ends up explaining nothing at all. Humans aren't equations. We're not consistent systems. We break. We contradict ourselves. We eat sandwiches even when we're unsure about the mustard. Gödel couldn't accept that. He needed the world to be as precise as his theorems. It never was. Some people say he was cursed by his own genius, that he thought so deeply he couldn't find his way back. Others say he was just a man in pain, in a world that didn't know how to help. And yet, his work changed everything. Gödel's logic redefined philosophy, mathematics, and computer science. He showed that there will always be gaps, always boundaries, always unknowns. He showed us that knowledge has limits, and that within those limits there's room for humility. So yeah, Gödel died of starvation, but his ideas, they're alive in every math class, every programming language, every debate about truth and meaning. It's the most paradoxical legacy. A man who couldn't trust the world left behind insights that made the world smarter. Sometimes brilliance comes at a cost. And sometimes the cost is everything. Next up, we'll turn the page from paranoia to patriotism, to codes, ciphers, and equations that changed the world. We're heading into World War II and the mind of Alan Turing. Coming next, Alan Turing and the equation that beat the Nazis. Let's take a break from starving logicians and infinite hotels and jump straight into World War II. Don't worry, it still involves math, lots of math, and one of the most fascinating minds of the 20th century, Alan Turing. Turing was British, brilliant, awkward, and about to change the course of history using something as old-fashioned as logic and as new as computation. During the war, the Nazis used a machine called the Enigma to encrypt their military messages. It was, at the time, considered unbreakable. The code changed every single day, millions of possible combinations. It was like trying to guess a password that rewrites itself every 24 hours. Enter Alan Turing, who basically looked at this terrifying puzzle and said, "Challenge accepted." He joined a secret team at Bletchley Park, the British code-breaking headquarters. While the rest of the world fought with tanks and planes, Turing fought with paper, gears, and theoretical math. His genius move? He realized you didn't need to break every code. You just needed to reduce the possibilities. Use logic. Find patterns. Use known words. Like weather or Heil Hitler, which, yes, was often in the messages. He designed a machine, a precursor to the modern computer, called the bomb. It ran through possible settings for the Enigma, trying to match outputs to real words. And it worked. Not instantly, but enough to give the Allies the edge. Historians estimate that cracking Enigma shortened the war by 2 to 4 years. Millions of lives were saved, and yet barely anyone knew Turing's name, because his work was classified. Top secret. He couldn't tell anyone what he'd done. No medals, no public parades, just silent. After the war, Turing kept working. He developed foundational ideas in computer science, algorithms, artificial intelligence, logic machines. The guy was thinking about machine learning when machines still had vacuum tubes. And then, everything fell apart. Turing was gay, and in 1952 that was illegal in the UK. He was arrested, charged with gross indecency. Given the choice between prison and chemical castration, he chose the latter. Not because it was easier, but because he wanted to keep working. The punishment wrecked his body, his mind, his ability to work. He lost his security clearance, his reputation. The man who helped defeat the Nazis was now being punished by his own country for who he was. In 1954, Alan Turing died. Officially, it was suicide. A half-eaten apple laced with cyanide. He was 41 years old. And yes, the Apple logo theory is a myth. But it's poetic, isn't it? It took decades for the UK to apologise. First came recognition, then a royal pardon, then a movie, then finally an apology from the government. But it was all long after the fact. Turing didn't just beat Enigma. He laid the groundwork for modern computing. Every time you open a laptop, swipe a screen, or ask your phone a question, you're using something built on his ideas. And yet, his life was a contradiction. A genius who helped save the world, destroyed by the very society he served. A man who made machines think, and was punished for loving honestly. There's a line from one of his letters that haunts people. Sometimes it is the people no one imagines anything of who do the things that no one can imagine. Turing imagined machines that could learn. He imagined a future where logic could solve impossible problems. And for a while he made that future real. Next up, we'll meet another mind, who lived in paradox. Not a machine builder, but a mystic, a dreamer, a man who said his equations came from a goddess, and who gambled everything on numbers. Coming up, the mathematician who gambled with his life. Ramanujan. Let's leave the icy streets of wartime England and head somewhere much warmer. Southern India. Early 1900s. A skinny kid scribbling equations on temple floors with chalk. His name? Srinivasa Ramanujan. And he didn't learn math the usual way. He wasn't trained at Cambridge, didn't grow up reading textbooks. He grew up reading one weird old math book that didn't explain how the answers worked, just gave the answer. But Ramanujan didn't seem to care. He didn't need proofs. He said his formulas came to him in dreams, sometimes fully formed, no steps, just answers, like cosmic downloads from another universe. He believed a goddess, Namagiri, was whispering math into his ear while he slept. And honestly, the math was so good, people started to wonder if she really was. He wrote hundreds of formulas, weird, beautiful, terrifying ones. Infinite series, continued fractions, identities that seemed to come out of nowhere. But no one in India's academic world knew what to do with him. He was a poor clerk, lived on rice and almost nothing else. No formal education, no degree, just notebooks filled with equations. No one understood, so he sent letters to professors in England. Most of them ignored him, or thought he was a crank. One even called it a fraud or a joke, but one man didn't. G.H. Hardy, a leading mathematician at Cambridge. He opened Ramanujan's letter, saw the formulas, and thought, this guy is either a genius or a lunatic, possibly both. Hardy invited him to Cambridge, but that was no small thing. Ramanujan was deeply religious. Crossing the ocean was taboo. He was vegetarian, sensitive to cold, and sickly even in warm climates. Still, he made the journey. All for math, a dangerous, uncomfortable, life-changing decision. He arrived in England in 1914 and immediately started blowing minds. Hardy said that working with Ramanujan was like being shown the answers to questions you didn't even know existed. His intuition was almost supernatural. He couldn't always prove things, but he was always right. And remember, this wasn't the internet era. There were no libraries in his village, no teachers, no calculators, just raw talent, and maybe a goddess. But the cold, the food, and the stress caught up with him. He got sick, over and over. Doctors didn't understand his diet. He didn't understand their medicine. Eventually, he returned to India, severely ill. He kept writing, kept dreaming. One of his last letters contained what are now called mock theta functions, ideas that would take decades to understand. Ramanujan died in 32 years. That's all he got. And in that time he produced nearly 4,000 theorems, some still being unpacked today. Hardy later said that discovering Ramanujan was the one romantic incident in his life. And when asked to rate mathematicians, Hardy placed himself as a solid 3. Ramanujan, a solid 1. Even today, Ramanujan's work shows up in physics, black hole theory, string theory. The math he dreamed, literally dreamed, is reshaping how we understand the universe. And here's the twist. Ramanujan never thought of math as just numbers. To him, every equation was an expression of the divine, a way to touch the infinite, to listen to something larger than logic. He once wrote, "An equation means nothing to me unless it expresses a thought of God." So yes, he gambled with his life. He left home, broke taboos, starved, suffered, all for math, all for truth, all for beauty. Next we'll shift gears again from mystical math to explosive math. Literally. Coming up, EEMC Quedu, the most dangerous equation in history. Let's take a deep breath. We've wandered through infinity, paranoia, mysticism, and machine code. Now we arrive at something small, simple, elegant. 3 symbols, 1 equation. EE. It's the most famous equation in history. So short it fits on a coffee mug. So powerful it helped build the most destructive force humankind has ever unleashed. Energy equals mass times the speed of light squared. Sounds chill. Let's break it down, not mathematically, but historically. This equation didn't appear out of nowhere. It came from a guy with wild hair, a bicycle, and some deeply rebellious ideas. Albert Einstein. In 1905, Einstein published a series of papers. One of them, just a side note really, suggested that mass and energy weren't separate things, they were different forms of the same thing, like water and ice, or pizza and happiness. This was revolutionary. Up until then, people thought mass was just mass, energy was just energy. Einstein was like, nope, they're connected, and not just connected, interchangeable. But here's the kicker. The conversion factor is huge. The speed of light squared is an enormous number, which means a little mass equals a whole lot of energy. That's the heart of nuclear reactions. Fission, fusion. You lose a tiny bit of mass, and you release an absurd amount of energy, enough to light a city, or flatten one. Einstein's equation sat quietly in physics books for a while. People admired it, quoted it, put it on blackboards to look smart. But it wasn't until the 1930s and 40s that it got terrifying. Scientists began to understand nuclear fission, splitting atoms, unlocking energy stored in the nucleus. And they remembered, oh right, that Einstein guy told us energy and mass are the same. So began the Manhattan Project, a secret race to turn math into power. Scientists gathered in deserts, worked in silence, calculated, tested, hoped. And in 1945 it happened. A mushroom cloud rose over New Mexico. A few weeks later, two more over Hiroshima and Nagasaki. EEMC Quetta wasn't just a theory anymore. It was a weapon. It was history. It was horror. Now, here's the weird thing. Einstein himself didn't work on the bomb. He hated war. He was a pacifist. But he also feared what the Nazis might do if they got there first. So he wrote a letter to President Roosevelt, urging the US to act. That letter helped start the Manhattan Project. Einstein later regretted it deeply. He said, "Had I known that the Germans would not succeed in producing an atomic bomb, I would have done nothing." So the most dangerous equation in history came from a man who didn't want it used, a man who believed in peace, and somehow helped unleash apocalypse. It's a paradox, just like the math we've seen before, truth wrapped in tragedy, logic that leads to loss. But EEMCAHO isn't just destruction, it's also beauty. It explains why the sun shines, why stars burn, why the universe glows. It shows that matter is never wasted, that energy moves, transforms, dances. Even in endings there's motion, even in death there's light. Einstein once said, "The most incomprehensible thing about the world is that it is comprehensible." This tiny equation, just 5 characters, helped us comprehend the power of matter itself, and reminded us to be careful with what we learn. So next time you see EEMC Quater on a bumper sticker or a t-shirt, just remember, it's not just clever branding, it's a quiet equation, with a very loud story. Coming up next, from atomic blasts to sound waves, the unlikely journey of a simple curve that helped build the internet. Next, how a simple curve created the internet. After nuclear explosions and divine math dreams, it's time to talk about something a bit more familiar, the internet. Yes, that magical, chaotic space where you can watch cat videos, read conspiracy theories, and accidentally order 300 glow sticks at 3 a.m. But beneath all of that, beneath the memes and the emails and the endless scroll, lies something very mathematical. A curve. A simple curve. The Fourier transform. Let's rewind. In the early 1800s, a French mathematician named Joseph Fourier was studying heat. Not the emotional kind. Literal, physical heat. He wanted to understand how it spread through objects. And he discovered something amazing. You could break down any complex pattern, like a heat wave or a sound wave, into a series of simple sine waves, wiggly curves, the mathematical version of stacking tiny building blocks to recreate a whole shape. This became known as Fourier analysis. It sounds fancy, but the idea is beautifully simple. Every signal, no matter how messy, can be seen as a combination of pure, smooth vibrations. Now fast forward 50 years, computers are starting to get serious. Engineers are figuring out how to send sound, video and data through wires, cables, air, and guess what? All those signals are just messy waves. So how do you compress them, clean them, analyze them? You break them down into sine waves using Fourier transforms. MP3s, Fourier, JPEGs, Fourier, Wi-Fi, Fourier. Your voice on a Zoom call sounding slightly robotic? Yep, that's a Fourier thing. The transform takes something messy like a scream or a Spotify song and turns it into a recipe, a precise list of frequencies, so the computer knows exactly how to store, send, or recreate it. In other words, when you stream your favorite playlist or watch a video online, you're not just enjoying content, you're listening to the ghost of a 19th century French guy whispering. Everything is waves. The math is elegant, powerful, and everywhere. It's hiding inside your phone, your headphones, your Netflix account. But no one ever thinks, yes, I'm really vibing to these Fourier coefficients. That's the beauty of it. Good math disappears into the background. It lets you live your life without knowing it's there, like plumbing or oxygen. And it's not just about fun stuff. Fourier transforms help doctors read brainwaves, help scientists detect earthquakes, help astronomers analyze starlight. It even shows up in security, modern encryption, signal processing. Without Fourier, your Wi-Fi would be a squeaky mess, and your FaceTime calls would look like a watercolor painting on fire. But here's the twist. Fourier's work was controversial when he published it. Some mathematicians said his approach wasn't rigorous enough, that he was just playing with formulas, that he didn't follow the rules. Sound familiar? Like so many others we've talked about, Fourier saw something true before the world was ready to believe it. And now, we literally live in the world he helped build. All from a curve, a wiggly little sine wave, multiplied and added up just right. So next time your internet cuts out and you start cursing the rotor, just remember somewhere deep in the code, a Fourier transform is quietly doing its job. It might not be glamorous, it might not go viral, but it's one of the reasons the modern world exists. Coming up next, we're leaving smooth curves behind and diving headfirst into chaos, strange systems, tiny causes, huge effects. Next, the equation that predicts chaos. Let's talk about chaos. Not the kind you find in your sock drawer, or in group chats that somehow contain 97 unread messages. No, we're talking about chaos in math. Real chaos. Predictable unpredictability. It all started innocently enough. In the 1960s, a meteorologist named Edward Lorenz was running weather simulations. He plugged in some numbers, left the machine running, and came back later, but something was off. The second run gave completely different results, even though he'd only changed the input slightly. Like ridiculously slightly. Like rounding a decimal. Turns out that tiny difference, less than 0.1%, cascaded through the system and produced a totally different forecast. That's when Lorenz said something legendary. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? And boom, the butterfly effect was born. Welcome to chaos theory, the study of systems that are deterministic but wildly sensitive to initial conditions. Translation: the rules are fixed, but the outcome can be bananas. The equation at the heart of this chaos was deceptively simple, a feedback loop, a value that changes over time, influenced by its previous value. Mathematically, it looked like a toy, but it behaved like a wild animal. This was the logistic map. It's not long. It fits on a napkin, but it creates patterns that never repeat, shapes that look like noise but are secretly full of structure. Fractals, bifurcations, chaos. Graph it, and it starts tame, then suddenly splits into madness. like a polite dinner that turns into karaoke and then a food fight. And here's the fun part. This kind of math isn't just for weather nerds. It shows up everywhere. Ecology, economics, biology, population models, traffic flows, planetary motion, even dripping faucets. Anything with feedback and change can behave chaotically. Even you, your heartbeat, your sleep cycles, your stock market choices. Yes, chaos is probably why you bought 3 pairs of identical pants last month. But chaos doesn't mean randomness. It means complexity, hidden order, beautiful structure, lurking inside mess. Look at a fractal. Zoom in, it repeats. Zoom in again. Still repeats. Infinite depth. From a simple rule, that's chaos. It doesn't shout. It whispers. One of the coolest things about chaos math is how visual it is. Draw it out, and you get spirals, lightning branches, coastlines, brain scans, things that look like art, but come from equations. And remember, all of this came from a guy trying to predict the weather. A job that, even today, is part science, part sorcery.
Lorentz changed the way we understand the universe. He showed us that tiny things matter, that small changes ripple outward, that perfect prediction is impossible, not because the math is wrong, but because life is messy.
The butterfly effect became pop culture gold. Movies, novels, self-help books, people quoting it at parties to sound deep. But underneath the cliché is something profound. Everything's connected, and everything's a little unpredictable. So what do we do with that? Do we freak out because we can't control everything? Or do we step back, breathe, and marvel at the patterns that still emerge? Because even in chaos, there's beauty. Even in noise, there's rhythm. Even when everything seems uncertain, there's math quietly humming underneath. And sometimes that math looks like a butterfly. Coming up next, from swirling storms to fragile humans, why mathematicians aren't great at staying alive. Next, why mathematicians are bad at staying alive. Let's get personal. Not emotionally personal, biologically personal. Today's question, why are mathematicians historically so bad at staying alive? Okay, that's a little dramatic, but when you look at the biographies, it's not exactly encouraging. Geniuses dying in duels, starving themselves, getting sick from cold weather and bad soup. There's a pattern here, a weird one. Mathematicians seem drawn to danger, or maybe danger is drawn to them. Let's investigate. Start with Évariste Galois, shot in a duel at 20. Then Gödel, starved himself out of paranoia. Turing, persecuted and driven to suicide. Ramanujan, dead by 32 from chronic illness. And that's not even getting into Cantor's breakdowns or Abel coughing himself into an early grave. So what's going on? Is math cursed? Does knowing too many theorems lower your immune system? Or is it something else? Let's break it down like a good proof. First, the obvious stuff. Many of these mathematicians lived in times when healthcare was basically soup and prayers. People didn't live long, especially if they were broke, exiled, or too obsessed to eat properly. And obsession is a key word here. Math is addictive, deeply. Once you see how the world fits together, it's hard to stop thinking about it. Some people chase money, some chase fame. Mathematicians chase elegance, simplicity, proof. But chasing proof can mean forgetting to chase food, or sleep, or social interaction. Mathematicians don't always win at work-life balance. Also, let's be honest, some of the smartest math minds were not exactly emotionally stable. Depression, anxiety, isolation. Genius often comes with cost, and when society doesn't understand you or punishes you, it makes everything worse. Add in some tragic coincidences, and you've got a pretty grim spreadsheet. And here's the twist. Many of them knew the risk. They joked about it. They lived with it. They just couldn't stop. Math wasn't a job. It was a calling, a compulsion. Paul Erdos once said, "A mathematician is a machine for turning coffee into theorems." That sounds cute, but he meant it. He lived out of a suitcase, slept on couches, took amphetamines to keep going, because stopping felt like dying. He lived into his 80s, but not exactly peacefully. When his friends bet him to stop taking stimulants for a month, he did it, and declared, "You've set mathematics back a month." That's the mindset. Not always healthy, but fascinating. Even today, mathematicians burn out, stay up too late, forget meals, get lost in problems. The world doesn't always reward quiet, obsessive thought. And math, for all its clarity, can feel lonely. But here's the uplifting part. For all the early deaths and nervous breakdowns, these people gave us something eternal. Their minds may have broken, their hearts may have failed, but their theorems, still alive, still glowing. Their names are carved into chalkboards, textbooks, and lecture halls. Not just because they were brilliant, but because they gave everything they had to an invisible truth. So yes, math can be hazardous to your health, but maybe that's the cost of touching something bigger than yourself. Something abstract, eternal, perfect. Next time you see a proof. Elegant, clean, surprising. Remember, someone might have lost sleep, health, or sanity to give it to you. And maybe send your local mathematician a sandwich, just in case. Coming up, when math stops being a career and starts being a religion, what happens when numbers become sacred? Next, when obsession becomes religion. Let's talk about obsession. Not the "I watched one Netflix episode and now it's 3 a.m. kind. We're talking about full-blown, mind-bending, life-consuming obsession. The kind that turns numbers into something sacred. Because for some mathematicians, math isn't just a profession. It's not even a passion. It's a faith, a calling, a spiritual practice. There's a reason people talk about the beauty of math, the elegance, the purity. For some, it's the closest thing they'll ever experience to the divine. Equations become scripture, proofs become prayers. Take Paul Erdos. He didn't believe in God exactly, but he talked about the book, a perfect book written by a divine being, where every mathematical truth was listed, elegantly, flawlessly. His goal in life? To discover entries from the book. He didn't want to invent math, he wanted to reveal it, like a prophet with a calculator. He called God SF, the supreme fascist, who sometimes withheld truths just to be annoying. It was weird, but also deeply funny, and oddly moving. Erdos gave away his money, lived out of a suitcase, had no house, no spouse, just collaborators. He published with hundreds of people, slept little, drank lots of coffee, took stimulants to keep working. He didn't chase wealth or fame. He chased elegance. He wanted to know what math already knew, like a monk chasing enlightenment, but with graphs. And he's not alone. Many mathematicians talk about math like it's alive, as if numbers are waiting to be found, not made, as if they exist, floating out there, independent of us. Platonism, they call it. The belief that mathematical truths are eternal, that we don't create math, we discover it, like explorers mapping a hidden universe. It's why some proofs are described as beautiful, or ugly. It's why some equations make people cry. Not because of the difficulty, but because of the clarity. There's a kind of holiness to it, an almost mystical pursuit. You search, you fail, you try again. You hope the universe will show you just one clean line of logic. Some people go on pilgrimages, others climb mountains. Mathematicians stare at chalkboards for 18 hours trying to prove Fermat's last theorem. And honestly, same vibe. But there's danger in obsession. When math becomes religion, it can also become isolation, pressure, despair. Because what if the proof never comes? What if the beauty never arrives? Some mathematicians break, others just burn out. There's no final enlightenment, just another conjecture, another coffee, another late night of staring into symbols, hoping they'll blink back. Still, the devotion is real, the reverence, the awe, the sense that this isn't just numbers, it's truth and order and meaning in a chaotic world. You might not pray to a function, but when you see a truly elegant proof, clean, clever, inevitable, it can feel like something more than logic. You see it, and for a second, the universe makes perfect sense. Then it's gone, and you're back to laundry, or taxes, or figuring out what day it is. So maybe math is a religion, or maybe it just attracts the same kind of soul. The seekers, the pattern finders, the ones who whisper to the cosmos and hope it whispers back. Coming up, we've talked about obsession. Now let's talk about the cost, the danger of knowing too much, the loneliness of seeing what others can't. Next, the mathematician's curse. To know too much, there's a strange thing that happens when you look too long at infinity, when you stare into pure logic for years, when you chase patterns so deep they begin to stare back. Some mathematicians say they start to see math everywhere, in the cracks on a wall, in the way leaves spiral on the ground, in the rhythm of traffic, in their dream. At first it's beautiful, like you've unlocked a new layer of reality. But sometimes it's too much. The world becomes numbers, equations, ratios. You stop seeing things. You start calculating them. This is the mathematician's curse. The feeling that you might understand everything and still feel lost. It's the loneliness of seeing patterns others don't. The burden of seeing too much order in a chaotic world. The anxiety of being sure the pieces fit, but not knowing where you fit in. It's why some mathematicians fall into existential spirals. Why Gödel starved himself. Why Cantor collapsed into breakdowns. Why some geniuses vanish into forests of unsolvable problems and don't come back. Because knowing too much can be heavy. Real heavy. Mathematics at its deepest starts to feel less like a tool and more like a mirror. One that doesn't reflect your face but your mind. Your flaws. Your fears, your limits. And sometimes the math tells you there are things you can never know. Like Gödel's incompleteness theorems, which basically say, no matter how smart you are, no system can prove itself fully from within. In other words, even math has blind spots. And if math has blind spots, what chance do the rest of us have? That idea, proof that certainty is impossible, shook the foundations of logic. It haunted Gödel. It still haunts philosophers today, because it means the search for truth might never end. The curse is realizing the quest for understanding is infinite. Beautiful, but infinite. It's why some mathematicians drift into philosophy, or theology, or poetry. When math runs out of answers, the soul starts asking questions. But don't worry, it's not all doom and gloom. Some embrace the curse. They laugh in the face of uncertainty. They treat the unknown not as a wall, but as an invitation to wonder, to explore, to play. Because yes, knowing too much can be lonely, but it can also be freeing. If there are always new mysteries, then there's always more to learn, more to love, more to dream about. Mathematics in the end is not about certainty. It's about curiosity, not about control, but about connection with the universe, with other minds, with something bigger than us. So if you ever feel like you're cursed with knowledge, just remember, you're also blessed with wonder. You see the world differently, and that's a gift. Coming up, we're near the end now, but before we say goodnight, let's zoom out. What did these brilliant, broken, beautiful people leave behind? Next, the final equation. What they left behind. We've travelled far, through revolutions and equations, through obsessions, breakdowns, explosions, and elegant little curves. Now we've arrived at the end, the final equation. But it's not on a chalkboard, it's not something we can write down, because it's not a single formula. It's what these people left behind. Think about it. Galois died in a duel. Gödel vanished into fear. Ramanujan saw math in visions. Turing cracked codes and paid the price. Erdos floated across the globe, chasing the book. And yet, we remember them, not for how they died, but for what they saw. We remember Galois, because he opened a new world in a single letter the night before his death. We remember Gödel, because he proved that even logic has shadows. We remember Cantor, because he showed us infinity comes in sizes. They were flawed, lonely, brilliant, but they touched something timeless, and they passed it on. That's the final equation. It's not E.M.C. Quarto or the Riemann hypothesis. It's this: a mind meets an idea, and something survives. The spark gets past, the pattern continues. A theorem becomes a lecture becomes a memory becomes a curiosity, and one day, someone, you, maybe wonders, wait, how does that work? And just like that, the chain continues. The equation lives on. You don't have to be a genius. You don't have to write proofs in jail or sleep on a chalkboard. All you have to do is wonder. Ask questions. See patterns where no one else looks. You're already part of the equation. These mathematicians didn't just give us answers. They gave us better questions. They reminded us that even in chaos, there's beauty. That even in confusion, there's structure. That even when everything feels uncertain, truth is still out there, waiting. And maybe that's why we tell their stories. Not just to learn math, but to feel less alone in our curiosity. To know that someone else stayed up too late wondering about infinity. That someone else drew spirals in the margins. That someone else stared into the unknown and smiled. The final equation isn't written in symbols. It's written in us. In our questions. In our laughter. In the way we fall in love with an idea so hard we forget to eat lunch. So, here's to the sleepless ones. The thinkers, the wanderers, the ones who tried to make sense of the world with nothing but logic and a little stubbornness. They didn't find all the answers, but they made it okay to ask the questions. And now, maybe it's your turn. Maybe you'll chase an idea no one else sees. Maybe you'll write something that makes someone's eyes light up. Maybe you'll find beauty in something small and let it change you. That's what they left behind. That's what we carry forward. And now, we sleep. You've traveled through centuries, through equations and obsessions, through infinite spirals and the minds of people who gave everything to understand something invisible. But now it's quiet. The chalkboards are blank, the numbers are resting. And maybe, just maybe, so are you. Mathematics can be loud, bursting with symbols and sparks, but it can also be calm, like a silent pattern, gently looping in the back of your mind. You don't need to prove anything tonight. You don't need to understand Gödel or memorize Fourier transforms. You just need to rest. Let your thoughts drift, like prime numbers spacing out across the number line. Let your heartbeat follow a soft rhythm, an elegant curve no one needs to graph. You've spent enough time wondering, enough time imagining Galois scribbling in candlelight, or Turing decoding secrets, or Cantor dreaming of infinite sets. You've walked through chaos, through beauty, through fear, through faith. You've touched something abstract, and somehow it felt real. That's the magic of math. It's not just numbers, it's the story of how humans tried to understand the universe and themselves. So tonight, forget the proofs. Forget the paradoxes. Let your mind wander like a random walk. Let it meander through sleepy equations and imaginary numbers that don't ask for answers. Close your eyes and imagine a simple line, drawn slowly across space. Maybe it curves. Maybe it loops. Maybe it goes on forever. It doesn't matter, because in the end, math is just a language. And like any good story, sometimes it's okay to leave the ending open. So breathe in, hold, breathe out. You don't have to solve anything now. You don't have to chase the final theorem or unlock the book. You're allowed to rest, to be a quiet variable in a calm, drifting equation. Let the constants keep their balance. Let the functions do their thing. You just be. Maybe tomorrow you'll feel curious again. Maybe you'll see patterns in the sky, or wonder why the world spins the way it does. But for now, just rest. The universe will still be here in the morning. The math will wait. It always does. So good night, fellow thinker. Good night, little paradox. Good night, you beautiful, curious, overactive mind. We'll find the answers another day. Sleep well.